Hi everyone, I'm Omar, and I'm here to present our work revisiting Minimax lower bounds in episodic reinforcement learning. This is joint work with Pierre, Ménard, Emilie, Kaufmann, and Michal, Valko. Studying regret and sample complexity bounds in reinforcement learning is important. Upper bounds tell us how good an algorithm is, and lower bounds tell us what is the best we can achieve. Here, we focus on the Minimax case, which considers the bounds in a worst-case scenario. Our contribution is that we provide unified, simple, and complete proofs of Minimax lower bounds for episodic RL under the regret, PAC, and best policy identification settings. One interesting thing is that we use a single class of hard MDPs, which might make it easier to draw connections between the different performance criteria. We consider an episodic MDP with S states, A actions, and horizon H, such that taking an action A in state S results in a reward RH of SA, bounded in 0, 1, and a transition to a next state S prime according to the distribution PH given SA. We focus on the stage-dependent case, or time inhomogeneous, where both the transition and rewards are allowed to change in each stage H of the episode. In reinforcement learning, an agent interacts with the MDP in episodes, indexed by T, where each episode has H stages, using a policy pi that gives the probability of choosing an action A in state S at stage H. The value of a policy pi in an MDP M is the expected value of the sum of the rewards obtained in each stage H. A reinforcement learning algorithm can be defined as a history-dependent policy, which is a sequence of policies pi t, where each pi t is the policy played in episode t, and it is allowed to depend on the data observed up to episode t-1. In the best policy identification setting, the algorithm is also equipped with a stopping time tau and a recommended policy pi hat. Now, we define the three performance criteria for which we provide lower bounds. The regret of an algorithm after t episodes is defined as the sum over all episodes of the difference between the value of the optimal policy and the value of the policy played by the algorithm at each episode t. An algorithm is said to be epsilon delta PAC for exploration, or PAC-MDP, if the number of times that it plays an epsilon suboptimal policy, called n epsilon, is bounded with probability at least 1 minus delta by a function that is polynomial in the relevant quantities, the number of states and actions, the horizon, 1 over epsilon, and the logarithm of 1 over delta. Its sample complexity is defined by n epsilon. Finally, we have the best policy identification setting. An algorithm is said to be PAC for BPI, best policy identification, if the policy returned after tau episodes is epsilon optimal, where tau is a stopping time defining the sample complexity of the algorithm. We find in the literature that the lower bound for the regret is square root of h cubed SAT, where t is the number of episodes, and for BPI and PAC, the lower bound scales with h squared SA divided by epsilon squared times log 1 over delta for the time homogeneous case, or stage-independent MDPs, and there's an extra factor h when the transitions are stage-dependent, or time inhomogeneous. However, there are some drawbacks in the proofs of these results. Some proofs are only sketched, and some use hard MDP instances behaving like parallel multi-armed bandit problems, and these require some extra assumptions which are not always clearly stated. Also, proofs for different settings use different hard MDP instances. Now let's look at the general strategy for proving the lower bounds, which is the following. First, we define a class C of hard MDP instances. In each of these MDPs, the optimal policy is hard to identify. Also, all instances are similar to each other, but they have different optimal policies. Then, we use change of distribution tools between two well-chosen MDPs in this class to obtain the lower bound. In our construction, we use MDP instances that behave as a single bandit with roughly HSA arms and reward scaling between 0 and H, capital H. To gain intuition, let's first consider the case where we have only 4 states. The agent starts in a waiting state SW, where it can choose to stay up to a stage H bar, after which the agent has to leave SW. From SW, the agent can only transition to a decision state S1, from which it can only reach 2 absorbing states, a good state with reward 1 and a bad state with reward 0. There's a single action A star in S1 that increases by epsilon the probability of reaching the good state, and this action must be taken at a specific stage at H prime. So intuitively, in order to maximize the rewards, the agent must choose the right moment to leave the waiting state, and then choose the good action A star at S1. This results in a total of H bar times A possible choices, which we can see as meta actions, defined by the moment where the agent leaves the waiting state and by the action that it takes in S1. Also, H bar is chosen so that the maximum sum of rewards in an episode scales with the horizon H. To generalize this construction to more than 4 states, we can arrange the remaining states in a tree structure such that the number of leaves is proportional to the number of states. Then, the agent is given the extra choice of which leaf of the tree it is going to, which results roughly in a total of HSA possible choices or meta actions. Using this construction, it is straightforward to obtain a regret bound by analogy with the Minimax lower bound proved for multi-armed bandits, which is given by the reward range times the square root of the number of arms times the number of rounds. Here, our number of arms is proportional to HSA, and the reward range is proportional to H, which gives the result. For best policy identification, we show that for any algorithm that's epsilon delta PAC for BPI, the expectation of its stopping time is lower bounded by h cubed SA divided by epsilon square times the logarithm of 1 over delta. As a corollary, you can also prove a lower bound of the same order for the PAC-MDP setting presented here. To present the proof idea of this BPI lower bound, we need some definitions. We define M0 as the reference MDP, where all actions are identical, and MA bar as the MDP whose optimal meta action is A bar. NA bar tau is the number of times that A bar is chosen up to episode tau, and we define the event where A bar is chosen by the recommended policy with probability higher than 1/2. If the algorithm is epsilon delta PAC for BPI, then the probability of this event in MA bar is larger than 1 minus delta. Using change of distribution tools between MA bar and the reference MDP M0, we can lower bound the expectation in M0 of the number of times that A bar is chosen by a term scaling with H squared divided by epsilon squared. Finally, summing over all meta actions, we lower bound the expectation of the stopping time, which is the sample complexity. One novelty here is that, contrary to previous proofs, we allow the algorithm to stop after a random time tau, and recommend a policy that might be stochastic. The table here summarizes the lower bounds, and our proofs can also be easily adapted to the time homogeneous case, where then transitions and rewards do not depend on the stage H. And to conclude, we provide simple, unified, and self-contained lower bound proofs in different settings, which can be useful as a reference and also to link different performance criteria. It may also help the derivation of lower bounds for harder cases, such as Lipschitz MDPs and non-stationary MDPs. And that's it. Thank you for your attention.